Welcome back. Welcome back to class 14. We're going to do another example. Here is example 5.5 from Cengel. This is acceleration of steam in a nozzle. So we have this nozzle, and I can't find my cursor. There it is. This nozzle right here. Here you go. We're using English units again. 250 psi A and 700 degrees Fahrenheit. It is steady state, and so it enters the nozzle with an inlet area of 0.2 square feet. The mass flow rate is 10 pounds mass per second. Steam leaves it at 200 psi. Boom. So it went from 250 to 200. And at the velocity of 900, so that's a fair amount more. Although, no, wait, they didn't tell us what it was coming in. The heat losses from the nozzle per unit mass is right here, right? So it's not insulated, so there could be some heat loss coming on right there. Estimated to be 1.2 BTUs per pound mass. Determine the inlet velocity. Okay, there you go. That's why it wasn't given, because that's what we're going to find. And the exit temperature of the steam. Great. So we will attempt to do this problem. And I'm not going to just attempt. We're going to do the problem. There you go. Focus on that pencil. All right, good. P1 equal to 50 psi. T1 equal to 700 degrees Fahrenheit. Area is equal to 0.2 square feet. And so we can enter table F.7.2. And if we do that, those values, let's come in here and go to F. And sorry, let me get rid of these. F7.2, because we want superheated. We're going to assume it's superheated. That's a good assumption. 250. So we're right in between. We're in between this one and this one. Would have been nice if they had done it. And we're also here at 700. And so we might want specific. I'm not sure if we need it or not. Specific volume. Specific volume. I said that with a sibilance going on. Sibilance. All right. So we want to have the average between this value and that value and that value and that value, because we want 250. We could also go to this wonderful website, which is irc.wisc.edu, and go to water and go to absolute pressure 250. I'm not 100% sure they're going to give us the same exact values, because this is often well, not often, but they have changed it in the past. I've noticed that there was a big change somewhere in the 90s, like 1997, I think. But anyway, you can go to enthalpy and get 1,371. Is that in the same range? 1,371. Yeah, right in between there. Sure. Okay. So I meant to bring this back up. Okay, so from here, we can get the specific volume. Like I said, I can't recall if I need this or not, but it might be worth getting it. These are cubic feet per pound mass. And then we also have H is equal to H1, 1,371.0 BTUs per pound mass. Our state, so this is state 1. State 2 is going to be P2 is equal to 200 psi. And the velocity is 900 feet per second. And then they also said that the Q loss, I guess I don't have to write all of these things down, but I'm trying to model what you should do if you're solving a problem. It's like, trying to get along, like, what can I find out? Now, what can I find out from this? Well, they gave me Did they give me the mass flow? You give this. They say 10. Yeah, right here, 10. I missed on that. There you go. There you go. They gave us the mass flow, so a lot of times that's, we don't want to get stuck because we didn't read the problem thoroughly. Anytime you have a hard time with the problem, maybe read it a couple more times, and that might run across to you. So let's see. I'm distracted by something. Velocity 1. We can find the velocity 1, right? So actually determine the inlet velocity, because we can find what the we can find the volumetric flow rate versus specific volume. I have that up above, which is also going to be the mass flow rate times. Whoops, excuse me, I made a mistake. I was distracted by something, right? By the area, right? So, which that right there can be found by taking the mass flow rate multiplied by the specific volume and divided by the area, right? So this is actually technically, I guess you might say, yeah, the conservation of mass, what we're seeing, continuity, what we're talking about. The mass flow rate has to be equal to the same in and out. Take 10 kilograms per pounds mass per second, excuse me, and we have this 2.803, so this could be cubic feet, right? So they're going to cubic feet per second. So 2.803, once we multiply it by that, and divide it by the area of 0.2 square feet, and we will come out with feet per second, which is 140.2 feet per second. All right, so we worked through this in a couple other problems. We can go back to the original equations, but we came back and said that this is true when, well, no. We have to make a mistake. We have to be careful here. This has heat loss. I'll go back to the original. Original equation for steady flow, no accumulation, is going to be Q dot minus W dot plus, and then I want summation of M dot, and then I go back to this H tot I minus summation of M dot H tot E, right? And by the tot, they mean not only the usual enthalpy, but also the kinetic energy and potential energy. So they're like the total, right, inside there, right? There's no work being done, but there is heat. And now generally this is heat in. So as using this, if this is not heat in, as in this case, it's heat out, it's going to be negative. And they gave it to us on a per mass basis. So setting this thing correctly, we would say negative M dot Q, right? So they gave us the Q right there, the Q out. But this Q is Q in. So if you're using Q out, you need to make it a negative. And so here we're going to go plus M dot, and then the total coming in. So that's going to be M dot H in plus 1/2 V in squared minus M dot times H exiting plus 1/2 V exiting squared. Okay, so here's where we're going to go ahead and address that this is going to influence the results. Note that the M dots all cancel out here. So rearranging for this thing, I'm going to start out with my H in. Did we look that up yet? Yeah, we did, right here. So we have 1,371.0 times the M dot's gone, I forgot, plus 1/2 V1 coming in. We have to be careful because this is units of BTUs, right? So you want to go back to a couple of videos before where I showed you the units conversion that you need to make when adding these two things together. We will put in what the inlet velocity is going to be, which we just found a second ago, 140.2 squared. But in order to get which will be a foot squared per second squared, in order to get that compatible with a BTU per pound mass, we need to divide by the mechanical equivalent of heat and by the conversion factor of pounds mass to pounds force, right? Which ends up being the same thing as gravity, but it's not really gravity. We're not really dividing by gravity, we're dividing a conversion factor. But what that does, it will be able to turn that feet squared per second squared into a BTU per pound mass. It's difficult to conceptually accept that. We're going to subtract out the 1.2 out of this, and then we're also going to, let's see, we're going to have HE right here, and then plus, and then here's what I was trying to think of. We're going to take that 900 squared and divide it by 778 and 32.2. And as I have done before, and I should always do, I like to take a look at what these in-between numbers are to see what the significance of the kinetic energy is to this, right? This already fairly small number compared to this, but what are these contributions? Could we ignore? That's a great question. Can we ignore this? Well, we can try to ignore lots of things. Here, okay, so this is 0.3923, so that's pretty small. It's comparable to that, yeah. This is probably going to be larger. 900 squared divided by 2 divided by the 778 and the 32.2 divided. And that's going to be 16.17. So that's definitely in the ballpark there. So we get to HE. And the HE is 1,354.0 BTUs per pound mass. And we were given, so this is the enthalpy after this process right here. And we were also told the pressure. So with the pressure and this enthalpy, we should be able to come up with what the outlet conditions are going to be. And we don't know, it's steam, so we don't quite know. I have it down where I went and I looked at these superheated tables, right? If we go to the superheated tables, and these are still them, right? And we were in, what do we say? 200 PSI? So it's right here, 200 PSI. Let's take a look at that. Let's get rid of here. Boom. I don't know why I have all these in here. I'm not going to save it, so when I get out of the thing. So anyway, we're in between, we're at 1,354. 1,300, there you go. We're in between there, somewhere between 600 and 700. So we can interpolate out of that. If you interpolate it, so, you know, we could be lazy, table F. 7.2 interpolate. We get T2 is equal to 661.7 degrees Fahrenheit. If you want to, right, to get this closer, you can come to here, and in English units, we said it was 200 PSIA, right? 200. And now we could take enthalpy, and I'll go, but I have to make sure it's in BTUs, right? Yeah, BTUs per pound mass, so we're good with that. 1,354, and good enough. Boom. And they're saying 661, 0.07, 198, so 0.08. So it agrees with us. That's good. So we can write down what our answers are. So A was to find the inlet velocity, and that was 140 feet per second. And B was the outlet temperature of 662, let's call it, Fahrenheit. And the end.